Software quality assurance as a discipline has evolved over several decades, and its history can be divided into long-term periods that reflect significant changes in technology, methodologies, and practices. These periods highlight the evolution of software testing from a manual ad hoc activity to a highly automated, AI-driven discipline. One may differentiate 5 important software quality assurance periods during the 20th century and 3 long-distance eras after the 21st century began. The primary objective during the debugging period revolved around detecting and resolving flaws, or bugs, within software programs. Unlike modern testing paradigms, which emphasize prevention and systematic validation, early efforts were predominantly centered on reactive debugging, locating and correcting errors after they manifested in the code. This period corresponds to the formative years of computing, a time when electronic computers transitioned from theoretical constructs to practical tools capable of executing programmed instructions. Software development was in its infancy, and structured approaches to quality assurance had yet to emerge. Testing, as a formal discipline, did not exist. Instead, the process was largely synonymous with debugging, an ad hoc trial-and-error method of ensuring that programs functioned as intended. The key characteristics of the debugging period are as follows. Developer-centric debugging. Since specialized testing roles had not yet been established, programmers themselves were responsible for verifying their code. Testing was an intrinsic part of the development cycle rather than a distinct stage. Absence of formalized tools and techniques. Unlike today's sophisticated testing frameworks, early debugging relied on manual inspection, print statements, and rudimentary diagnostic methods. There were no automated testing suites, standardized methodologies, or dedicated quality assurance teams. Basic reliability as the primary goal. The chief measure of success was whether a program executed without crashes or glaring inaccuracies in output. The concept of comprehensive validation, such as edge case analysis, performance benchmarking, or user experience evaluation, was not yet a consideration. The main milestones of the debugging period are bug and debugging notions. In 1947, the terms bug and debugging were coined when engineers working on the Harvard Mark II computer discovered an actual moth had got stuck in a relay, causing it not to make contact. Grace Murray Hopper detailed the incident in the work log, pasting the moth with tape as evidence and referring to the moth as the bug causing the error, and to the action of eliminating the error as debugging. Reactive problem-solving mindset. Debugging was perceived as a corrective measure rather than a preventive one. Developers addressed issues only after they arose, often in response to observable failures, rather than proactively designing tests to uncover hidden defects. This nascent stage of software testing laid the groundwork for future advancements in quality assurance. At that time, the tests were focused on the hardware because it was not as developed as today, and its reliability was essential for the proper functioning of the software. While primitive by contemporary standards, the emphasis on debugging established the foundational principle that software must be scrutinized for errors, a concept that would later evolve into systematic testing methodologies, specialized tools, and dedicated QA professions. The central objective of the demonstration period shifted toward proving that the software operated in strict accordance with its intended design and specifications. Unlike the earlier era, where testing was synonymous with reactive debugging, this period emphasized validation, ensuring that the software not only ran without errors but also fulfilled its predefined functional requirements. As software systems expanded in scale, functionality, and criticality, the limitations of ad hoc debugging became increasingly apparent. Organizations recognized that merely eliminating crashes was insufficient. Software now needed to meet business and operational needs for sure. This era saw the gradual transition from informal developer-led error fixing to a more structured, though still nascent, effort to verify software correctness. Testing remained relatively informal compared to modern standards, but its purpose evolved, shifting from defect correction to requirement validation. The focus was no longer solely on making the program work, but on demonstrating that it worked as expected under defined conditions. The key characteristics of the demonstration period are as follows. Validation-centric approach. Testing was primarily employed to affirm that the software executed its intended functions correctly, rather than aggressively uncovering hidden flaws. The mindset leaned toward confirmation. Does it work as specified? Rather than investigation, where does it fail? Defect-avoiding mindset. The emphasis was on proving the absence of critical defects, often leading to optimistic assessments. Unlike later methodologies that actively sought weaknesses, for instance, stress testing, boundary analysis, etc., This approach assumed correctness unless evidence proved otherwise. Late-stage testing. Testing was frequently conducted toward the end of development, often as a final checkpoint before release. This test-last mentality contrasted with modern iterative testing, where evaluation occurs continuously throughout the development lifecycle. Manual and ad hoc execution. Despite the growing need for validation, testing lacked standardized methodologies or automation. Most checks were performed manually, relying on developer intuition or rudimentary test cases. The major milestones of the demonstration period are: tests development. In 1957, Charles Baker explained the necessity for test development aimed at ensuring the software meets its pre-designed requirements. Thus, the distinction between software functionality control, debugging, and software quality maintenance, testing, was introduced for the testing to be carried out as a separate activity. Tests' higher importance. Test development became more important as more expensive and complex applications were being developed, and the cost of solving all these deficiencies affected a clear risk to the profitability of the project. A special focus was placed on increasing the quantity and quality of tests. For the first time, the quality of an application began to be linked to the state of the testing stage. The goal of testing was to demonstrate that the software performed what it had initially been designated for, using expected and recognizable parameters. Emergence of verification and validation, V&V, the distinction between verification, are we building the product right? And validation, are we building the right product? Began to take shape. This framework laid the groundwork for later quality assurance disciplines. Continued reliance on manual processes. While the philosophy of testing matured, practices remained labor-intensive and unstructured. The absence of systematic test design, for instance, test plans, coverage metrics, meant that effectiveness varied widely across projects. The demonstration period represented a critical transition, moving software quality assurance from reactive debugging toward deliberate validation. However, the lack of formalized processes and early testing integration meant that many latent defects still escaped detection until deployment. These gaps would later drive the development of methodical testing frameworks, automated tools, and proactive quality measures to bridge the debugging and modern testing in subsequent eras. The destruction period represented a fundamental transformation in software quality assurance approach, where the primary objective evolved from proving correctness to actively seeking and exposing defects. Testing was no longer viewed merely as a validation step, but rather as a systematic effort to stress, challenge, and intentionally break the software under controlled conditions. The underlying premise was that improving software quality required aggressively identifying weaknesses before release, rather than passively confirming functionality. As software systems grew more sophisticated and became more mission-critical, the limitations of traditional verification-focused testing became apparent. A proactive defect hunting mindset emerged, recognizing that software reliability could not be assumed, it had to be rigorously challenged. The absence of observed failures did not equate to correctness. Flaws often lay hidden in untested scenarios. Human psychology influenced testing effectiveness. Developers naturally avoided tests that might break their code. The destruction period marked the professionalization of testing as a distinct discipline, shifting from an optimistic demonstration of functionality to a pessimistic, investigative process aimed at uncovering faults. The key characteristics of the destruction period are: formalization of testing. Testing transitioned from an informal post-development activity to a structured stage integrated into the software development lifecycle. Dedicated test cases, plans, and documentation became standard, ensuring systematic evaluation rather than ad hoc checks. Methodical testing techniques. Some techniques represented early efforts to systematize test design, moving beyond trial and error, were initially introduced during the destruction period. Boundary value analysis, BVA, focused on testing at the edges of input ranges, where defects frequently cluster. Equivalence partitioning, reduced redundancy by grouping inputs that should trigger similar behaviors, optimizing test coverage. Defect maximization objective. The success of testing was measured by its ability to expose flaws, not just confirm expected behavior. This required creative, adversarial thinking, crafting scenarios that exploited potential weaknesses in logic, input handling, or edge cases. Proactive mindset. Testing was no longer about waiting for failures to emerge in production, but preemptively forcing failures in development. This shift reduced the cost and risk of late-stage defect discovery. The major milestones of the destruction period are: software testing definition. In 1979, Glenford Myers, with a definition below, radically redefined the procedure for detecting faults in the program. Software testing is the process of running a program with the intention of finding errors. Myers' concern was that in pursuing the goal of demonstrating that a program is flawless, one could subconsciously select test data that has a low probability of causing program failures, whereas if the goal is to demonstrate that a program is flawed, our test data will have a greater probability of detecting them and we will be more successful in testing and thus in software quality. From now on, the tests will try to demonstrate that a program does not work as it should, contrary to how it was done until then. This reorientation laid the groundwork for modern testing theory, prioritizing defect detection over confirmation, leading to new techniques of testing and analysis. Destructive testing methodologies. Myers' philosophy spurred the development of new techniques explicitly designed to expose hidden assumptions in code, challenge error handling robustness, reveal edge case vulnerabilities. Testing was no longer a passive checkpoint, but an active quality improvement mechanism. The destruction period permanently altered software engineering practices by establishing core principles that endure today. Testing must be skeptical, assuming defects exist until proven otherwise. Quality is achieved through rigorous challenge, not just affirmation. Test design is a distinct skill, requiring specialized knowledge beyond coding proficiency. The introduction of structured techniques, boundary value analysis, equivalence partitioning, etc., and Myers' psychological insights formed the foundation for subsequent advancements in automated testing, risk-based testing, and continuous quality assurance. The evaluation period represented a fundamental transformation in how the software industry conceptualized and implemented quality control. Rather than treating testing as a final gatekeeping activity, organizations began embracing a comprehensive philosophy of continuous quality evaluation spanning the entire software development lifecycle. This paradigm shift moved quality considerations from being reactive to being proactive, from being fragmented to being integrated, from being defect-focused to being quality-centric. By the early 1980s, several converging factors necessitated this evolution. Increasing software complexity in business and mission-critical systems, rising costs associated with post-release defect remediation, growing recognition that quality cannot be tested in, but must be built into the process. Maturing understanding of software engineering as a disciplined practice. The software industry transitioned its view on testing from separate stage to an integrated process, from defect detection tool to a quality assurance mechanism, from final verification step to a continuous evaluation practice. The key characteristics of the evaluation period are as follows. Life cycle-wide quality assessment. Quality evaluation became embedded in every software development lifecycle stage. Testability verification in requirements analysis. Architectural reviews in design. Unit testing in development. System testing in deployment. Regression testing in maintenance. The development gained a V-shaped prominence, explicitly mapping test activities to each development stage. Formalization of testing practices. Standardized methodologies emerged. Test documentation became mandatory. Metrics and measurements were instituted and developed. Specialized QA roles and departments appeared. Quality assurance as an organizational function. Quality assurance became distinct from testing, encompassing process definition and improvement, prevention-oriented activities, organizational quality culture, metrics and benchmarking. The quality gate concept institutionalized checkpoints throughout the software development lifecycle where specific quality criteria must be met before a project can progress to the next stage. Process-driven testing approach. Repeatable test processes replaced ad hoc methods. Test planning became forward-looking rather than reactive. Traceability matrices linked requirements to test cases. Formal entry and exit criteria governed test stages. The major milestones of the evaluation period are: in 1983, IEEE 829 standard for software test documentation established uniform documentation requirements including test plan structure, test case specifications, test procedure definitions, test log requirements, incident reporting formats, test summary reporting. The standard introduced a common language for test professionals, enabling process consistency across organizations. The advent of automated testing tools was another significant achievement of the evaluation period when Early test automation frameworks emerged. Regression testing became practical at scale. The foundation for modern continuous testing was laid. Institutionalization of quality metrics introduced. Defect density measurements. Test coverage percentages. Requirements traceability matrix. Escape defect analysis. These provided quantitative quality assessments. Legacy and transition to modern practices. The evaluation period established foundational concepts that continue to shape quality practices today. The principle that quality is a process, not an event. The understanding that testing must be planned and managed. The recognition that quality requires organizational commitment. The framework for integrating testing throughout development. This era's emphasis on standardization, documentation, and process orientation directly enabled the subsequent innovations. Capability maturity model integration. Agile testing methodologies. Continuous integration and continuous delivery pipelines. DevOps quality practices. The institutionalization of quality assurance during the evaluation period transformed software testing from a technical afterthought to a professional engineering discipline, establishing patterns and practices that remain relevant for decades later. The prevention period marked a paradigm shift in software quality management, transitioning from reactive defect detection to proactive defect prevention. The industry recognized that finding bugs late in the software development cycle was costly and inefficient, leading to a strategic emphasis on early testing, rigorous process controls, and continuous improvement. Testing evolved from being a post-development checkpoint to an integrated, iterative practice embedded throughout the software development lifecycle, SDLC. The goal was no longer just to identify flaws, but to prevent them from occurring in the first place through systematic process enhancements and early validation. Several key factors drove this transformation. Increasing software complexity. As applications grew larger and more interconnected, late-stage defect resolution became prohibitively expensive. Cost of late defects. Studies showed that bugs found after the software release were from 10 to 100 times more expensive to fix than those caught early. Demand for faster releases. The emergence of internet-driven business models necessitated shorter development cycles, making traditional test-last approaches obsolete. Maturity of software engineering. The discipline began adopting formalized best practices inspired by manufacturing quality control. This period saw the professionalization of testing as a strategic function, rather than a tactical afterthought. The key characteristics of the prevention period are early and continuous testing, or shift-left. Testing activities moved as early as possible in the SDLC with the relevant practices introduced. Requirements reviews, formal inspections to ensure clarity, completeness, and testability before coding began. Design inspections, rigorous evaluation of architectural decisions for potential flaws. Code walkthroughs and peer reviews, collaborative defect prevention via manual code analysis. The practices led to reduced rework by catching ambiguities and design flaws before implementation. Process-centric quality assurance. Quality gates, that is mandatory checkpoints at the end of each stage, to enforce standards. Standardized methodologies. Adoption of frameworks like Capability Maturity Model and Agile Iterative Development which enabled continuous feedback via incremental testing. Metrics-driven improvement. Defect density, escape rates, and test coverage became key performance indicators. Tooling and automation advancements. Static analysis tools. Automated code review for early defect detection, for instance, linting tools. Test automation frameworks. Dedicated software testing automation and software quality assurance products emerged. CI and CD precursors. Early continuous integration and continuous development tools enabled frequent validation. Cultural shift toward quality ownership. Shared responsibility. Developers, testers, and business analysts collaborated on quality. Prevention mindset. Teams focused on getting it right the first time rather than relying on downstream testing. The major milestones of the prevention period are formalization of shift-left testing. Testing early and often principle became a cornerstone of modern SDLCs and influenced later methodologies like continuous testing. Rise of Agile Iterative Development. Scrum, since 1995, and Extreme Programming, since 1996, methodologies embedded testing into short cycles. Test-driven development, TDD, emerged as a prevention-focused practice. Growth of testing tools and frameworks. Industry standards expansion. ISO 9003, since 1997, provided QA guidelines for software development. IEEE 1012, since 1998, introduced standardized verification and validation processes. The prevention period laid the groundwork for the future software quality assurance process enhancements. DevOps, merging development and operations with quality as a shared goal. ShiftRight, complementing early testing with production monitoring. Quality engineering, beyond testing, encompassing design for quality principles. This period's emphasis on prevention, automation, and process discipline remains central to contemporary software engineering, proving that proactive quality assurance is far more effective than reactive debugging. The first decade of the 21st century marked a transformative period in software quality assurance, characterized by the widespread adoption of automation and the emergence of new testing paradigms. As software systems grew in complexity and release cycles accelerated, manual testing became increasingly impractical. This period saw the industrialization of testing through automation frameworks, agile-aligned methodologies, and early AI-assisted tools, laying the foundation for modern DevOps and continuous testing practices. Several key drivers fueled the shift to systematic and intelligent testing focused on efficiency and scalability. Explosion of web applications. The dot-com boom and Web 2.0 demanded cross-browser compatibility and 24/7 reliability. Agile adoption. Shorter development cycles required faster feedback loops via automation. Cost pressure. Studies showed automation could reduce regression testing effort by more than a half. API-centric architectures. Service-oriented architecture made API testing a critical need. The key innovations and methodologies of the automation testing period are: test-driven development, TDD, writing tests before code greatly reduced defect rates, forcing modular and testable software design. Behavior-driven development, BDD, bridged business IT gaps using natural language specifications using human-readable syntax, aligned testing with user stories, and enabled non-technical stakeholders to validate logic. The Selenium revolution. Since 2004, Selenium WebDriver allowed browser automation with cross-browser support and language-agnostic bindings, which made it the de facto standard for web UI testing. API testing maturity. The shift from UI-centric to API validation enabled early, shifted left, integration testing and performance benchmarking. Cloud-based testing platforms eliminated lab maintenance costs and provided real device testing, which is critical for mobile development. The automation period transformed testing from a manual job to a strategic, tech-driven discipline, proving that quality at speed was achievable through innovation. The period between 2012 and 2021 marked a revolutionary shift in software development and testing, driven by the widespread adoption of DevOps principles and continuous testing. This era was defined by the convergence of development, testing, and operations, transforming traditionally isolated functions into a collaborative, automated pipeline. The primary goal was to accelerate software delivery while maintaining high quality, achieved through automation, infrastructure innovation, and cultural change. Several industry trends necessitated this evolution. Demand for faster releases. The rise of cloud computing and software-as-a-service models required continuous deployment, that is, code daily or hourly released. Microservices architecture. Distributed systems increased complexity, making end-to-end testing more challenging. Agile at scale. Large organizations adopted Scrum, Kanban, and other agile frameworks requiring testing to keep pace with rapid iterations. Cost of manual processes. Manual testing bottlenecks appeared to significantly delay releases. This period saw the death of the throw-it-over-the-wall mentality, replacing it with shared ownership of quality. Shift left, or early testing. Testing moved earlier in the SDLC, with developers writing unit tests, integration tests, and API tests alongside code. Test-driven development, TDD, and behavior-driven development, BDD, became standard in agile teams. ShiftRight, or production testing, extended testing into production via real user monitoring, A/B testing, and other techniques. Infrastructure as code. Containerization tools, such as Docker, since 2013, revolutionized testing by packaging apps and dependencies into lightweight, portable containers, enabling consistent test environments, eliminating works on my machine issues. Orchestration tools, such as Kubernetes, since 2014, automated container governance, allowing scalable test clusters. Infrastructure as code tools, such as Terraform, Ansible, automated environment provisioning, reducing setup time from days to minutes. CI/CD pipelines and automated testing, continuous integration and continuous development tools allowed automating local and in-cloud build test deploy cycles. Parallel test execution across environments. Site reliability engineering emerged, blending operations and quality assurance. This period democratized testing, making it every engineer's responsibility rather than a QA-only task. It transformed testing from a slow manual process to a fast, automated, and intelligent practice. By integrating testing into CI/CD, infrastructure, and monitoring, it laid the groundwork for today's autonomous, AI-enhanced practices, giving the birth for continuous quality. Continuous testing became a necessity rather than an option, ensuring that software kept pace with the demands for rapid delivery and high user expectations. It proved that speed and quality are not trade-offs, but mutually achievable goals. During the current testing period, artificial intelligence and machine learning are fundamentally redefining how testing is conceived, executed, and optimized. AI-driven testing, or AI-powered testing, is the use of artificial intelligence and machine learning to automate and enhance software testing processes. No longer confined to scripted validations, testing has evolved into an intelligent, predictive, and self-improving process that spans the entire software lifecycle. Several converging trends have accelerated this transformation. AI maturation. Breakthroughs in deep learning enabled practical applications beyond research labs. Testing complexity crisis. With systems becoming more complex, traditional methods became economically unsustainable. Generative AI explosion. The 2022 ChatGPT release proved AI's potential to create test artifacts, not just analyze them. Key technologies behind AI-driven testing are: machine learning improves test scripts over time by learning from past executions. Natural language processing converts plain text requirements into automated test cases. Computer vision uses image recognition for UI testing, for instance, identifying dynamic elements. Predictive analytics identifies high-risk areas needing more testing. The major milestones of the AI-driven testing period are: self-healing test automation. Traditional tests broke due to dynamic UI, environment inconsistencies, and flaky network conditions. AI tools use machine learning to detect when element locators change, automatically update selectors while maintaining test intent, learn from corrections to improve future resilience. This reduces test maintenance, enabling sustainable automation at scale. Visual validation with computer vision. Traditional tools validated HTML structure. Visual AI tools use convolutional neural networks to detect visual regressions at pixel level and ignore non-impactful changes. ML-powered test impact analysis. Machine learning tools can analyze code changes via static analysis, map modifications to affected test cases, prioritize test execution based on historical defect data, code complexity metrics, and business criticality. Codeless automation tools lower the automation barrier the following ways: use natural language processing to translate plain languages to test scripts, provide visual modeling interfaces, auto-generate maintenance scripts. As a result, codeless automation enables subject matter experts to create tests, reduces automation skills gap, accelerates test coverage expansion. The current era does not just change how we test, but what it means to deliver quality software in an AI-driven world. The organizations thriving in this new paradigm are those treating quality as a strategic differentiator rather than a compliance checkpoint. Unlike traditional scripted automation, AI-driven testing leverages intelligent algorithms to generate test cases, self-heal test scripts, predict defects, optimize test coverage, analyze test outputs. As a result, the most obvious benefits of AI-driven testing are: faster test creation. AI generates tests from requirements or user behavior. Reduced maintenance. Self-healing tests minimize script updates. Smarter test execution. Prioritizes critical test cases. Improved accuracy. Reduces false positives and negatives. Enhanced test coverage. AI explores edge cases humans might miss. While not a complete replacement for human testers, AI significantly reduces manual effort and improves software reliability. AI will not replace testers in the nearest future. But testers who use AI may definitely replace those who don't.